Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, question 26 states, when 1 kilogram of coal is burned, approximately 3.0 times 10 to the 7 joules of energy is released. If the energy released during each fusion of uranium-235 is 2.0 times 10 to the 2 MeV, again, per fission, so I'm calling that per N, or per number of decays, whichever you choose. The question does ask, how many kilograms of coal must be burned to produce the same energy as 1 kilogram of uranium-235? Okay, so we're told a couple of things here. That we have, if we have a mass of 1 kilogram of uranium, we know that the energy released per mass of coal. So I guess maybe I'll clarify here, this is for coal. If the energy released during a uranium fission, so this Q over N is energy per uranium, we need to know how many kilograms of coal. So when you're looking for a mass, I'll call this of coal, is what we're trying to solve for. But we're assuming that we want to know how much energy, well, how many kilograms of coal must be burned to produce the same energy as this expression here. Right, so we need to know a couple of things about what we're dealing with. First of which, we want to find out how much energy is burned when we burn 1 kilogram of coal. So the energy burned for this, for uranium. It has to deal with uranium, right? How much energy do we burn when we burn 1 kilogram of uranium? Well, we can simply find that to be the charge per, not the charge, this is not charge anymore. Excuse me, is the energy per fission multiplied by the number of fissions that will occur with 1 kilogram of uranium. So if we know the rate per fission, 2.0 times 10 to the 2 MeV per fission reaction. Well, how many fissions occur? I'm going to do this on the side here. Well, we know we're dealing with 1 kilogram of uranium. So the number of fissions that would occur, we think back to our chemistry, deal with these elements. So if we're given a specific mass, the number of atoms present or fissions would be the mass over the, which I'm calling capital M, the molar mass, multiplied by Avogadro's number, should give us the number of atoms that we're dealing with. So I'm going to substitute this in. We'll check our units as we go. So we have 1,000 grams, right, for 1 kilogram. That's our M term here. So just so I'm obvious, this term is being substituted in here. So we have 1,000 grams. Our molar mass will take to be what we have for uranium, 235.0439. That should be sufficient precision for this question. We know the molar mass gives the mass in terms of grams per mole. And we know Avogadro's number, 6.022 times 10 to the 23 atoms per mole. Or I won't say atoms, I'll say fissions, or a number of particles, whichever you choose, but it's N per mole. So this means that if we look at what we have, our grams cancel out here, 1 over mole on our denominator cancels out the moles here, our number of fissions cancels out here, and we're left with MeV. Looking ahead, I do deal with mass in terms of joules, so I'm going to convert this right away from MeV to joules. So I know that 1.6 times 10 to the negative 13 is the amount of joules per 1 MeV. So as a final unit check, my MEVs cancel out, and I do produce an energy in terms of joules. So this is the amount of energy produced in one burning, burn uranium. This is the amount of energy produced from 1 kilogram of uranium. And so multiplying this out, I find I get 8.2 times 10 to the 13 joules. Great. So this is my total energy, what I'll call U, or total energy for uranium. And finally, the question does ask, if I want to find the total mass of coal, MC, looking at what I have, if I take the ratio, well, maybe I should have said here, in my initial statement, the units for my coal over Q over M, so that's joules per kilogram, although notice that is not a dose, that's just the amount of energy burned per kilogram, or created, I should say. So we can solve for what the mass is if we take our total energy in terms of from uranium, divide that by our Q over M from coal, which is solves for the mass. Because our energy terms cancel out, because we want these energy terms to be equivalent, and we do pop out this mass value. So we find, using our energy we found from uranium, 1 kilogram of uranium, I should say, 10 to the 13 joules. We can divide that by our energy per kilogram, 3.0 times 10 to the 7 joules per kilogram of coal burned. Our units of joules cancel. We're left with units of kilograms. And we find that we would need 2.7, again, two significant figures, 2.7 times 10 to the 6 kilograms of coal. So a huge amount of coal would be required to match the 1 kilogram output, or 1 kilogram of energy. 1 kilogram of uranium produces the same amount of energy as 2.7 times 10 to the 6 kilograms of coal, showing that nuclear energy, while is much more energy efficient, or much more supply efficient, to produce the same amount of energy.